So this is a great quote for just teaching chemistry in general. Science may be described as the art of a systematic oversimplification, the art of discerning what we may, or the art of discerning what we may with advantage omit. So a lot of times there's stuff that you want to leave out because it just overcomplicates things. And if you're trying to understand something, especially for the first time or at an overall level, looking for a particular meme here that explains this, it's often way more helpful to look at a simplified model to learn things rather than trying to dive into the deep end right off the bat. This is one example of why you might want to do, when it's up there, you'll see. There we go. I know things are misspelled. I didn't make this. All right, so why do you always wear that mask? This mask of weird rules and exceptions. It's because quantum physics is ultimately the reason. You got to go deep into some really hairy math if you want to be able to explain all of those. A lot of times, yeah, there's fewer weird rules and exceptions than there is physics to actually learn to explain these things. So that's the goal. All right, solubility of ionic compounds. We're going to look at this, at least at first, from a qualitative point of view. Does it dissolve or does it not dissolve? Ionic compounds, we just talked about electrolytes. When an ionic compound dissolves in water, the resulting solution contains separated ions. We're talking metal and nonmetal, dissolves in water because the water is stronger than the bonds between the metal and its nonmetal. If something dissolves, we would say it's soluble, and insoluble if it does not. Although, to a certain extent, everything dissolves, even if it's quote unquote insoluble, there's a teeny tiny amount that will dissolve. To cover that in a lot more depth in Chem 2. So we call this process dissociation. So when an ionic compound dissolves, we get ions and cations get separated. We would write that out this way. So here we got sodium sulfide, 2 sodium ions. We get out 2 sodium ions and then 1 sulfide ion. In polyatomic ions, and this is another reason, again, to remember and memorize polyatomic ions, the sulfate stays as sulfate. It's an oxyanion. And so when it dissociates, we get 2 sodiums, but sulfate as the other ion, the anion. So some things dissolve, some things don't. Silver nitrate dissolves in water just fine, forms a strong electrolyte. Nitrate is one of the ones, I'll show you, I think it's on the next slide or two, but in the qualitative rules, there's some that are just good to remember. Nitrate's one of them. Nitrate, when it forms compounds, always soluble. No exceptions. You got to do some very complicated stuff to get an insoluble complex of nitrate. Silver chloride, on the other hand, is almost completely insoluble. So actually for your potassium chlorate lab, that chloride test, or the test that you did for potassium chloride was using silver nitrate because you add silver, and when silver finds a chloride ion, it becomes an insoluble compound and forms that white precipitate that you should have seen. So almost completely insoluble. So how can you know when a salt will dissolve or when it won't? Really not easy to predict, especially not at a Chem 1 level. So we do things very qualitatively, and you get a table, and that table tells you what dissolves and what doesn't, basically. And you can develop some sort of rules to guide your predictions on whether or not something will dissolve. This is an empirical method. So basically, somebody took a bunch of different cations and a bunch of different anions and mixed them together. Actually, it was one of the experiments in Chem 20. And you determine whether or not certain things are soluble or insoluble. This is the table that the book will give you. And I'm actually going to give you a different table. But in general, these are the ones that you just want to memorize because there are no exceptions. So these alkali metals, lithium, sodium, potassium, nothing becomes insoluble. And ammonium, or ammonia. And then nitrate, like I mentioned before, and also acetate. So like these are the ones that it's just useful to remember that those don't form any insoluble compounds. Everything else is generally going to have exceptions. And of course, somebody let me know if Alex breaks one of these rules at any point. So just to look at the way that this table works, in case it works better with the way your brain works. These first are generally soluble. So anything with chloride, bromide, and iodide in general will be soluble. And then there's the unless mixed with, so the exceptions. So for those ones, it's going to be silver, mercury, really it's 1+, but mercury 2+, and then lead will make insoluble compounds with those. On the other end, I don't need to go through all these. These are ones that you should also remember. Hydroxide and sulfide for the insoluble compounds. Because for the most part, the exceptions are lithium, sodium, potassium, and ammonium. Sulfide, though, will form soluble compounds with calcium, strontium, and barium, alkali earth metals, second group. And hydroxide with calcium, strontium, and barium also will be slightly soluble. So those are the ones that sort of get into that gray area of there is a certain amount of anything that will dissolve in water. And so again, this table is all about, most of the time these things are insoluble, sometimes they're not, these are the sometimes. Okay, this is the table that I'm going to give you. Oh wait, what? Okay, I copied over the wrong slides apparently. This is like the only thing that I added. How do I want to do this? Cool. It's not a big fan of me doing that, but. Okay, so this is the table that I'm going to give you. I'm just going to erase these things that are covering it. To me, this table is a lot easier to read, even though it might look more complicated. So you have cations, so positively charged ions. You have negatively charged ions, going this way, going that way. So you find your positively charged ion, let's say we're doing aluminum, and then you go down the row. Aluminum acetate forms a solid, so S here is solid. So that's a solid. Aluminum bromide, that's aqueous with chloride and chlorate. Fluoride is going to be another solid, right? So you find your cation, you find your anion, find where the lines cross. The only thing that I think trips people up on this chart is just make sure you know the difference between like sulfate and sulfide and sulfite. Okay, so did I make a Mentimeter slide for this? I did. Nice. Okay. So I'm going to leave this up here because you can go onto Mentimeter and it has each of the compounds. But I will show you just real quick. So this is what you should see on Mentimeter. Yeah, does that. Modified a sliding scale thing, so there's only one or two. Does it show you the results on your phone or no? After you like enter something? Okay. Yeah, slide 7, sorry. If you're not on Mentimeter, it's on slide 7. Oh, right here. NIS MG3PO42 2CO3. It's just Li2CO3. Oh, I don't think I finished writing the last one. Yeah, I know. I forgot to write the Cl in there. Yeah, is ammonium by itself soluble? Yeah, even if you just said ammonium, you could probably make a guess. It's aqueous with everything. Okay. So make sure that you're not getting tripped by the S means solid, the AQ means aqueous. So I guess this is just showing overall averages. Is there a way to, no. 12 and 3, 12 and 3, 2 and 13, 2 and 13. Interesting. So what we're looking for on this chart, so nickel and sulfide, So we go nickel, whoops, nickel. And then we would say sulfide. And so where they cross, nickel and sulfide, that's S, so that should be solid or insoluble. And then for magnesium phosphate, so magnesium, draw a line all the way across, then phosphate coming down. That's also S, that's a solid. Now lithium is again one that's really good to know because, ooh, there's an exception. Phosphate, actually. So lithium, with pretty much anything, is going to be soluble, so it's aqueous. Oops. I guess I said soluble or insoluble. Why? Because somebody did the test and it was soluble. It might be a definition of what constitutes soluble or insoluble. Because again, everything dissolves some. Yeah. So that's why I'm saying it might be a different definition of at what limit, like how much of it has to dissolve or not dissolve before I say it is soluble or insoluble. Here they have actually a definition listed. Compounds having solubility of 0.1 mole or more in 1 liter of water at 20 degrees C are listed as soluble. So it must be less than 0.1 mole, which maybe the book just says. Anyways, I'm going to give you this chart on tests and stuff. So yeah, maybe. If I give you the chart. And then ammonium chloride is going to be insoluble. I'll have to look up what the actual solubilities of lithium phosphate is. Chloride, so soluble. Any questions about how to read this? No? Again, just make sure you're getting, if you want sulfate or sulfide or sulfite, make sure you're picking the right row. Okay. So that was for this. I guess I'll write them in. Insoluble. There. Right, okay, so you need to know that for predicting precipitation reactions. I think no, that might have been Chem 20. Briefly mentioned them in Chem 20. This is one use though, they'll put carbonate, other compounds in laundry detergent. Oh, it's on the slide, I don't need to remember that. Laundry detergent, so that it causes these precipitates to form because those ions can interfere with how well the soap works. So it precipitates them out. This is also the thing that causes hard water deposits on sinks and faucets and the like. And ultimately what a precipitation reaction is, you're taking two usually clear solutions, transparent, you can see through them. It doesn't matter if it has a color, but if you can see through it, generally things are going to be soluble in those solutions. But when you mix them, you'll get cloudiness, either colored precipitate like this, or sometimes white precipitate. It can be any color. In the copper cycle lab, you saw a bunch of different precipitates there, right? When you first add the sodium hydroxide, you get that dark blue precipitate. Then you heat it up and it turns into a black precipitate. You dissolve it and then actually eventually precipitate out the copper. So we're mixing two aqueous solutions and getting out something that's solid. And so this is why you need to have a chart or memorize solubilities so that you can predict if the two things you mix are going to produce a solid. Not that we talked about in this class. Yeah, we mean Chem 2. Talk a little bit, crystal field theory. It has to do with how the light interacts with the different compounds and mostly about how their electron structures interact with different ions. So you can get certain solutions that change with, I guess the color affects the equilibrium and they change colors depending on temperature. Is that like neon? Oh, neon signs? How you can get different colors? That's a different property, but also has to do with the electrons and how they interact with the electricity being passed through them and releasing that extra energy as light. Ultimately, it all comes back to electrons for most things. Okay, so if you want to predict a precipitation reaction, basically you got to come up with all of your options. Now this is where it's important to remember that you can, in ionic compounds, you have to have a positive and a negative. You can't have two positive ions mixed together because, right, positive and positive, same charge, same sign, they will repel each other. Can't have two negative ions because the same thing, they repel each other. Really, whenever you're mixing two things, if our original compounds here were potassium and iodide, or potassium iodide, I should say, and lead nitrate, the only new combinations are to swap anions or swap cations, depending on how you look at it. Right? I cannot make potassium lead compound. That doesn't work. And I can't have an iodide nitrate compound because they're both negative charges. These are also called double displacement reactions. Okay, so now on this one, if we swap these, then we get two new possible products, potassium nitrate and lead iodide. So is potassium nitrate soluble or insoluble? Soluble. So it's going to be aqueous lead iodide. In a sense, yeah. You're going to have two reactants. You could have more than just two. Like it's a little more complicated. Okay, so lead iodide, let's go back to the chart. Actually, wait, maybe I can, cool. Just make another one appear. And then zoom. Enhance. Okay, so lead, specifically lead 2. Wow, that's real thick. You do it like this. So we got lead, and then we're looking for iodide, and where those cross is an S, which is a solid. So you can write over here, solid. We haven't talked about it yet, but does a reaction happen here? Yes? No? Yes? Yeah, something happens, right? When I mix those two together, and I should send this picture here, the lead iodide precipitates. So we get some cloud of something that would form. Might be clear. I think this one's actually yellow. But it's cloudiness that's going to appear in the solution. And because of that, now all these lead iodides are no longer really in the solution. They're part of that mixture, but they're not in solution. They're not dissolved. Now, of course, that doesn't always happen. So if you take your two reactants, here we got potassium iodide and sodium chloride. If we mix those, the way we should do this is you should always swap. So the way I like to do this actually, and we'll do more examples of course, but right, so potassium and sodium, I like to swap the anions. I write the cations in the same order, and then we'll swap the anions. The chloride goes over here, and the iodide goes over here. We would say, okay, potassium chloride, is that soluble or insoluble? Soluble. Let's maybe stick with aqueous or solid. It'd be aqueous. And then sodium iodide, also aqueous. So neither of those forms a solid. So when I mix these two solutions, all that's really happening is now I've got 4 different ions in the mix instead of 2 in each. And we would see nothing happen. So that's why this would be no reaction. So if you look at your 2 ions, if your new ions don't form a solid, no reaction. You just got more ions. Okay, so writing equations for precipitation reactions. Oh, it's 611. Okay, write the formulas for the 2 reactants. Then below, write the formulas of the products that could form. So that's what I just did there, where I wrote the cations in the same order, swap the anions. Then you use your solubility rules to determine if any of those possible products are going to be insoluble or solids. If both possible or all the possible products are soluble, write no reaction. That's the easiest one. You don't have to do anything else. If any of the products are insoluble, then you've got to write the formulas of the products and then balance. And it doesn't really put it in here as a step, but you also got to make sure that your formulas for your new products are also balanced. Oh boy, we get to use nomenclature. Ammonium chloride. What's ammonium? NH4 plus. And then chloride, just Cl minus. So that's going to be our first one, NH4 plus. Well, sorry, NH4 plus. Cl minus is just going to be NH4Cl. That's ammonium chloride. Aqueous. Iron 3 nitrate. So iron is Fe, and which charge? 3 plus. And nitrate? NO3 minus. So what would be the correct formula for lead nitrate then? Or iron, sorry. Yeah, Fe, NO3, 3. Okay, so now we want to know if we even have a reaction. So let's see, lead. Why do I keep saying lead? It's iron. So I'll write my cations down here in the same order. And then I'll swap my anions. And at this point, we're not going to worry about balancing any of these formulas yet, because we need to figure out if we even need to do that extra work or if we can just write no reaction. Ammonium nitrate. It's got nitrate in it. Nitrate's always soluble. This will be aqueous. But iron 3 chloride. So we go to iron 3 and chloride, and oh, it's aqueous. So what does that mean? Woohoo! No reaction. Yep. Okay. How about for, this is really annoying. Sodium hydroxide. Na, and hydroxide is OH. And then copper bromide. Cu, and actually for this one, might want to write it out this way, 2 plus. Bromide is just going to be Br minus Cu, aqueous. So then my possible combinations. Again, this step right here helps prevent you from making further mistakes, because just writing one of them in the same order makes it a lot easier to think about just swapping one. All right, so you swap the cations, or swap the anions. So Br minus, and then this is copper OH minus. And I can magically summon this chart again. So copper 2 hydroxide. Copper 2 hydroxide. S. So that means it's solid, which means I need to now move this out of the way. So these will be at least the template for our products then, because, sorry, this one's aqueous. This one's solid. So we can just write the NaBr minus, or sorry, NaBr. That's still aqueous. But then for the copper hydroxide, copper's a 2 plus, hydroxide's a 1 minus, so I need 2 hydroxides. And then there's one more thing to do. Is this balanced? Nope. Does it matter what we balance first? Actually, these are probably the easiest ones to balance, because it doesn't really matter what you start with. So if it doesn't matter, then start left to right. So I'll start with sodium first. If you say, oh, sodium's balanced, right? It's 1 and 1. I'll go to hydroxide. Is hydroxide balanced? Nope. So I gotta add a 2 here. Now, when you're starting, just go left to right. But now I've changed the coefficient for sodium hydroxide, which means that I balanced my hydroxides. Now there's 2 there and there's 2 here. But I changed my number of sodiums. How do I fix that? To there, and then what does that change? It is balanced now. But it also changed bromide, so then I check my bromides and I say I got 2 of those, 2 bromides there, and then while I'm at it, copper, 1 copper. So just follow your changes. Every time you add a coefficient in one of these double displacement reactions, it's always going to change the thing that you want to balance and something else. And the something else is you just follow that and make any changes as you need to, and usually you end up in just a few steps working through every element to completely balance it. Okay, that's pretty much it for those precipitation reactions. It's really just using the chart or remembering which things are soluble, which things are insoluble, solid or aqueous. If everything's still aqueous, then there's no reaction. Oh, I didn't put, oh, these are the other slides. The other thing I did was, because we covered complete ionic equations and net ionic equations already. So for a reaction that has a solid in it, for our complete ionic equation, we'll write that still with the solid together because they're not separating into ions. Anything that's aqueous and not a weak acid will separate out into its ions. And then for the net ionic equation, again, also review here. All of the stuff that doesn't change, those are spectator ions. We call them spectators because they're just watching the other things react. They get canceled out. Because our net ionic equation is essentially the simplest way to depict this reaction, the thing that's actually happening. Depending on what else is in solution, sometimes though, the net ionic equation, yeah. If I added something else to my reaction mixture here, all of these ions, we canceled them out because they're spectators. They're still in that mixture though. They're still floating around. So if I had something that could react with potassium or react with nitrate, then I could get another reaction to happen in addition to the lead and chloride forming lead chloride. This also illustrates if I mix 2 things and everything ends up as aqueous and split into ions. So if I didn't have this lead chloride, if it was lead ions and chloride ions, then everything would be a spectator ion. They would all cancel out, and that's why it's no reaction, because nothing changed. 620. No, okay, that's probably as good a stopping point as any.